Okay, so this is the real reason I started this channel. I wanted to share this. This is time integration in Blender 3.4. It doesn't require the experimental version of Blender that has simulation nodes in it. I did see some videos out there on that, and it looks like it's maybe a little unstable right now. Eventually it'll get worked out, and a lot of the things I do in here can be used once those features are available in the regular download of Blender. So until then, we can use this ping pong method in order to do the same thing. Now, the pong is basically you're passing through some variables, and here I have the object that's input is ping, and then this displacement and velocity attributes are just passed through. Now, you can't connect input to output directly, so I had to fake it with a putting it into an add node and then connecting them and then getting rid of the add node when I connected them directly. And also under the geometry nodes, the object, you need to put the displacement and velocity on those inputs, and also the outputs, you need to put displacement and velocity. If they're not there, you need to type them in. Now the ping, we'll look at the geometry nodes modifier first, and it's the same thing. You need to have displacements in, velocity in, displacement out, velocity out. And ping is actually started with a cube, and what I did, I went into, and here I'll do it, I got a cube, I went into edit mode, and then I just merged all the nodes at center. And here I'll turn on the screencast so you can see that. All I'm doing is hitting M, merging them at the center, so I just have one node in that whole, that's the only thing there. There's just that one point. So let me get rid of that cube and do all that. So now I'll go into a little bit of the theory behind it. And if you want a good book on this, Strogatz has a book called Nonlinear Dynamics and Chaos that goes over some of these. And you can find that online. If you go to any site, you can pick up a version of it if you want. So the time integration, and let me explain what this is. Let me get my tablet situated and turn on annotations so I can write this out. So this is Euler's method. And Euler was a guy, he died in like 1780s, something like that. So this is a pretty old method, and it's kind of interesting that someone from so long ago came up with this, and it's still useful today. So Euler's method is based on a system where you have the time derivative of x, some function of x, and then at time equals 0, x equals x naught, which is the initial condition. And for when I'm writing these are really matrix and vector quantities. So if I have velocity and displacement, that's a vector. And I'll show you what that looks like in a little bit. So Euler's method says that if we're looking at time 0 and the next increment, which is time, which is time 1, then x of t naught plus delta t equals x1, and that's equal to x naught plus f, the function that defines x, f of x naught times delta t. Now this isn't a very accurate way of integrating the there's an improved method, and that's something that I mentioned in an earlier video. There's also Runkutta, but I wanted to start off simple before I get too far along, so that's why I'm going over this. In general form, it's x of n plus 1 equals xn plus f of xn times delta t. So our system here is a mass spring system, And if you look at another one of my previous videos, I do a derivation, and this is the equation of motion of the mass spring system. So that's mass times acceleration plus damping times velocity plus stiffness times displacement is equal to the forcing. And so if you rearrange the equation, you get x double dot equals minus k over m times x minus c over m x dot plus 1 over m times f. So if I rewrite this into what they call state space form, which is a matrix way of describing this, you can see that this is the form of the equation. So the top is just basically saying that x dot equals x dot. And then the second row is the equation that we rewrote before. So the Euler method, I'm saying that xn plus 1 equals xn plus f of xn times delta t. And then also in terms of velocity, we have x dot n plus 1 equals xn dot plus f of xn dot times delta t. So then I have my functions, my fxn is equal to basically x of n. And my function f of x dot n is equal to that whole mess on the bottom, which is minus k over mx minus c over m x dot plus 1 over m f. So that's what I'm implementing in this method. Okay, so this is the node group that defines this method. So you can see, I'll kind of walk you through it. I have kind of hard-coded C, M, and K, and you can see that as you follow the math through it, it's C over M, and then there's minus C over M, there's K divided by M, and then that's multiplied by -1, so you get minus that quantity. And then that's multiplied by x of n, and then the minus c over m is multiplied by x dot of n, and then those two quantities are added, and then that's also added to our function, but actually I'm zeroing out that function, so it's there in case we want to do something with it later, but it's 0 for now, so there's no forcing, just like the example problems that I've done up to now. So then that quantity at the bottom is multiplied by delta t, and then it's added to x dot of n, and that becomes x dot of n plus 1. And then the x n plus 1 is a simpler quantity, and that's just delta t times x dot of n, and then that's added to x of n. So that was our first equation, which is basically just x of n plus 1 equals x of n plus x dot of n delta t. And so that's it. That's the Euler's method. So, I need to erase some of this. I didn't realize it would pass on through. Okay, so we'll start here. I'm reading in frames, and then I'm checking to see, and this is a compare node, and I want it so that I have a 0 at the first frame. so I need to subtract 1. And also I want to create some switches that are going to go from initial values to the values that are sort of propagated through the loop that we're creating. And it's important that this is an integer, and you set this to 1. So then you can see what I'm doing with it here at the first switch, and this object is actually Pong, so it's reading in whatever Pong is outputting. And that's basically what the ping pong does. Ping goes to Pong, and Pong goes to ping, and back and forth as you go through time, or as you go through each frame. We're not in real time here. We're in each frame is a time increment, so there's not a one-to-one correspondence. So the geometry that is the basic model is read in if the switch is true. If it's false, then it's reading that propagated quantity. So that's where the geometry comes from. And then also for the initial conditions, I have a similar switch. These both need to be float because it's a float going in, and I have the initial displacement 0, the initial velocity is 1. And then again, if it's true, which means you're at the first frame, then you set it to the initial value. If it's false, then you read the propagated value. And then here on the bottom, I'm just subtracting 1 from the first frame, from the frame number, and then multiplying that by delta t. So I get my time is n minus 1 times delta t. So that's my time. And n is my frame number. So here's my forcing 0. I just have a 0 there. And then what I'm doing is I'm taking this output, which is x of n, and then the other output from the switch, that's x dot of n, and what comes out of those is what we just went through, which is x of n plus 1 and x dot of n plus 1. And then what I'm doing, I'm taking the geometry and using a capture attribute set to float. So I'm taking the initial the geometry that's being changed and putting that into there, and then outputting that attribute with the capture attribute node and making that the displacement. And then also the velocity that comes out, I feed that geometry into another capture attribute set to float point, and then I'm saying that is the velocity. So that's the x dot n plus 1 that goes into that one. And then we're feeding it into the velocity, and that's what's output. Now, in order to do something with this geometry, that's the point, I have a set position, and here I'm setting the position to 0, and then the offset of that is what I'm putting in. So I'm taking the displacement, and here I have some multiplication values, and that's just to get it on the same scale as the plot that I output from Python. And I was showing that in an earlier video. And then time is going into the second one, as you can see here. So I'm just plotting out time and displacement just like I was in Python, and that's combined. So I have y is time and z is the displacement, and then that goes into the offset. And then that all goes into the geometry output. So here I have my inputs and my outputs, and then also on Pong I have my inputs and outputs there. So I also created an icosphere, and all I'm doing there is in the ping model, I created a group, and if you go into edit mode, you can add vertices into groups, and I only have one vertex, and so I added that to a group. And then icosphere, I did a copy location constraint, and the target is ping and the vertex group is group. And when I do that, and of course I scaled the icosphere down from the default size that it usually is. And so what it's going to do is the icosphere is going to follow whatever that ping output is. So it just gives me something that's a little bigger than a single point, something I can follow a little more readily. And so that's basically it. So like I said at the beginning, this is really why I wanted to put a video out there. I wanted to share this, and hopefully, this can spur on some neat projects by other Blender users out there. If you do anything cool, please send a comment and share it with other people that are interested in this. And I hope you enjoy it. Have some fun. All right, bye.